Let's continue our discussion of plotting. I am on slide 9 of the plotting intro slideshow. In this case, we're going to move away from line plots to create a histogram, and we needed a little bit more complex data. So I built up a dictionary, and then I dumped that dictionary into a data frame. The dictionary is delimited by the curly braces that we've come to know and love, and then a series of comma-separated key value pairs define the information in the dictionary. After we've converted it to a data frame, we can create a histogram from part of that data frame. And as always, let's go back to our notebook. I added in a additional import statement, which, to be clean and follow our general standards, should be at the top. But as I'm developing these notebooks, sometimes I find the need and I throw it in there, which is not the best idea. I admit it should be at the top. So my data frame has name, age, gender, number of children, and number of pets. Somebody has 5 pets. That's a lot. And I immediately feed it into the data frame constructor, part of the pandas library. That data frame then is returned to me as a reference, and I store that into my variable df. Let's print that out. You know what? Let's break this up a little. Let's take the plotting logic out of that cell and put it into a separate cell. Sometimes it's helpful to logically break up the code that way. We have that luxury in JupyterLab. And now I can run the cell that sets up my working environment, creates my data, but I'm going to hold off on the excitement of creating the plot just yet. The data frame has columns that can correspond to the keys in the key value pairs of the original dictionary. Name, age, gender, state, number of children, number of pets. The data frame constructor put together a default index of numeric values starting at 0. And it's not sorted. It's simply in the physical order that was presented by the dictionary. That gives me some level of confidence that I have the data that I think I have. Notice that the values in that dictionary are lists, and the lists are comma-separated data which become a column. So each row has a name, an age, a gender, a state, a number of children, and a number of pets. I can't stand the excitement anymore. Let's run the plot logic. The first thing I did was create a figure. Give me a place to put my plot. Added a subplot. Now this subplot takes up the entire figure. It's a 1-by-1 array of subplots. So there's nothing else that I can put into this figure right now. And then I create a histogram only on the age column. So I'm ignoring most of the data, but I want to see the distribution of ages across my data frame. And all I do then is pass that column by name. Scroll up a little, you can see we have a column called age. If I refer to that column using indexing syntax, then I get that entire column, which as we know is a series. And I let matplotlib or matplotlib automatically decide what the bin should look like. So again, it's doing a lot of the heavy lifting for me. And then I did a little bit of formatting with colors. I asked for green histogram bars and black around the outside of the bars. And I can see then that it created a histogram from approximately, I don't know, 18 to 33 perhaps. And there appear to be 5 people in that range. I guess that would probably be 19. And I can visually verify that there are 5 people in that range. All the way out to the far right of the histogram, there appear to be one person between, about 63 and 78, 79. And there's that person right there. So again, with just a couple of keystrokes, we're able to build up a interesting representation of our data. Let's try it with a different set of bins rather than letting the hist function decide. And I'm going to look at the documentation for matplotlib.pyplot.hist. You'll notice we invoke that by saying ax1.hist because we already had a place to plot. So it doesn't look quite like this, but it's still the function that we need. So what I'm concerned about then is the bins argument. This is a keyword argument, meaning that I label it by saying bins equal, followed by my bin values. And I don't have to worry about what order these come in. As long as the first argument is my data, which they represent by x, the rest of these arguments are optional and can be provided in any order because they're labeled. So they're not positional arguments, they're keyword arguments. The bin can be a list. The list can define the beginning and the end points of the bins proceeding from left to right along the x-axis. And there's some explanation here of what is inclusive and what is exclusive, but generally the second number is the end point of the bin, which is not inclusive. So 1, 2 means go from 1 and then stop before you get to 2. Or as the page says here, including 1 but excluding 2. And then the very last argument is inclusive. So 3 to 4 means including 3 and including all the way to 4. And then there are some other options that you can specify. I used auto in the first example to let the histogram function decide what the bins look like. I'm going to go ahead and put in my own, put in my own set, my own list. And I'm going to start at 0. And I'm going to say I want to go to 13. Let's go 14. So I'm going to go, we'll leave it at 13. So I want everybody who's until they're a teenager. That's going to be one bin. And then I'll go from 13 to 22. So I'm going to get everybody who's 21 years of age down to 13, because remember that limit is not inclusive. And then I'll go 30. That's kind of a milestone in people's ages. And from there I'll just go in increments of 10, 40, 50, 60, 70. I'll go all the way to 80, even though there aren't any 80s, but there is a 78 though, so I need to get to 80 to get that last person. And remember, this is a list, so I delimit it with square brackets. And then the hist function parses that list and uses those as the boundaries for the bins. And let's see what I get now. There we go. Now that shows me that there is nobody in the data set that is under 13. So there are no, everybody is at least a teenager. And there are two people from 13 to 21. There are two people from 22 to 29. There's one person from 30 to 40, 30 to 39. There's one person from 30 to 39. There's one person from 40 to 49. There's nobody from 50 all the way up to 69. One person between 70 and 79. So I don't know the algorithm that HIST uses to determine the bins, but here's a way you can get your own spin on that using some contextual knowledge of people's ages and trying to break it up into some logical sets. Let's look at what the HIST function returns to us. So I'm going to add to the beginning of this call, I'm going to say just data. Now HIST will do its thing, generate the plot, and then return to us some information, and we will catch that information and store it in the variable data. And then I'm going to print that out. Now when I print that out, pay close attention to what's already there. When I ran it last time, just a couple moments ago, it dumped out the histogram in the figure, but it also dumped out a bunch of other information, which, as we're going to see in a moment, is what we're going to have available to us in that data variable. Let me just add a print statement here. And the reason for doing this is so that rather than having it just dump out to the screen, I have access to it and I can manipulate it if necessary. So printing it is moderately interesting, but having the ability to drill down into it has value to me. So I'm going to say print data. You're going to see again that what's already here, what already printed the last time I ran this, looks very much like what I'm about to do in this explicit print statement. So run the cell. There it is. Pretty much the same thing. And we don't know what that is. Let's dig down to it and let's say print type data. That's a start anyway. I got a whole bunch of information there, and I'm going to start by trying to figure out what Python thinks that data represents, and I'll just click run again. It says that it's a tuple. Okay, well, a tuple is just a container. It's just a way of grouping things together like a list or a dictionary. You can see it's in parentheses. Therefore, there's another giveaway that it's a tuple. And if you stare at it long enough, it might start to look familiar. The second argument, the second value in the tuple is my bin designations. And the first argument happens to be, if you looked at it long enough, you'd probably recognize the number of data points that appear in each bin. You can see from 0 to 12, the first bin, there were no data points, and that shows up as a 0. And the next two bins each had 2 data points, then followed by 2 bins of 1 data point, 2 empty bins, which are right here between 50 and 69, and then 1 in the 70 to 79 bin. And if we look at the documentation from Matplotlib, it tells us that it returns 3 things, and we saw that those 3 things are grouped into a tuple. That's the way that Python returns multiple things from a function, is by putting them into a container such as a tuple. And it tells us what those 3 things are. The first of which is what the count is, the data point count for each bin, going from right to left to right, sorry, left to right. The second is the size of the bins. And we know what that is already because we defined those. We didn't let the hist function decide what the bins look like. So the second argument looks just like our bins argument that we passed to hist. And the third argument I'm not completely familiar with. It looks to be something we could use to draw on each bin. And I have no other experience with that. But I can take this data and just to give you some experience at manipulating it, I could go for each, and as soon as I typed that, I realized it was wrong. So for, let's say, P in data sub 0. Whoops. There we go. I'm saying now that I only want the first element in that tuple. Back to the documentation again, the first element in the tuple is the values of the bins, how many data points appeared in each bin. I'm going to step through that set of information, the first element in the tuple, and I'll just print them out because we love to print things, don't we? Print P. Run the whole cell again. I get the plot again. I get all kinds of cool stuff. There it is right there. And you can see then that I have direct access programmatically to the number of data points in the bin as computed by the hist function. I didn't have to do any work. I let the histogram function decide where the points were, and then it came back and told me what the result was. And I could programmatically then, let's modify this again. I can say look for the max value across the bins. In other words, which bin had the most data points in it? Which bin was highest or tallest? Again, I'm doing things programmatically rather than having to stare at the graph and figure it out. And can I do a max on that? Can I say print max data sub 0? Remember, data sub 0 is the first element in the tuple returned from the function. And the documentation tells us that that is the value of the histogram bins, which I've been calling the number of data points in the bin. And will I get a 2? I hope I do. Let's see what I get. Let's make this a little more friendly. The max bin count is, comma. There we go. And I did get a 2. And that tells me that either one or more of the bins had 2 data points in it. All right, let's move back to the slides again and continue our discussion. We will be on slide 10. In this example, we're going to put 3 plots in the same subplot figure, in the same subplot of a figure, and then save it to the disk. Now, I feel almost uncomfortable telling you what we're going to do and then showing you that it only takes one line of code. But that's part of the power of Python, is there are a lot of things that in other languages might take a little bit longer code-wise that can be done in one line of code. I'm just going to grab all of this because I'm so excited to show it to you. Back to my notebook. So in this case, I'm going back to the line plot again, and I'm going to plot 4 points. Not that exciting. Give the plot a label, and then save it. Now when I do the save fig, it doesn't generate any output in the notebook. It simply writes it to the file name that you've given. So let's see what happens there. You'll notice I already have that file. I'm going to delete it. I don't have it anymore. When I run this now, it should create myplot.png. There it is. Seconds ago it was created. Now I can look at that. I don't know if the notebook will open that for me. If I double click on it, yeah, it does. So the notebook is capable of opening a PNG file, which is roughly analogous to a JPEG if you've ever used JPEGs. And there's my plot. I could also go to Windows Explorer and navigate into that folder and then open that file with Photos or Paint or whatever graphics tool that I like to use. Now this is a little bit different than some other utilities that I've used in that I have to provide that 3-letter file extension. So sometimes, and I know Paint is a good example of this, if you save something out of Paint, it will automatically assume a file type and automatically put that extension on there for you. But in this case, you've got to provide it yourself. So it's not a big deal, but it's a little different from what you might be used to in other utilities. The next thing I did in this cell was create another range of data. In this case, I'm arbitrarily calling it time, 200 millisecond intervals of time, which that's not evident here, but we'll say that for the sake of discussion. And then I plot 3 different plots on the same graph in one call to the plot function. And all I'm plotting is t against itself, so my range of values against itself. And then I'm plotting t against the square of itself. And then finally t against the cube of itself. So t star star 2 is t squared, t star star 3 is t cubed. And then I'm asking for red dashes in the first plot. I'm asking for blue squares in the second plot. BS is blue squares. Then I'm asking for green triangles in the third plot. That one shows up in the notebook because I called show after I executed the plot. What do you think happens if I try to save this new plot? Call save fig again. Let's use the same file name, myplot.png. In most situations, we get a warning, correct? This file already exists. Would you like to overwrite it? Or would you like to cancel the operation? What does this do? Well, it didn't give me any kind of feedback. And my plot says 4 minutes ago. And it hasn't been 4 minutes since I ran this. It's only been a few seconds. So what do I get? It's blank. How about that, huh? It's a little confusing, isn't it? What if I comment out all this stuff up above? All I have now is the attempt to create those 3 line plots in a single figure, followed by a call to show and then a call to save. I don't have any of the other work that I had above that. And let's run this cell again. Now I get my 3 line plots, and you may have noticed that this still says a minute, and now it's just jumped to seconds ago. It's a little bit slow to catch up, but is there a file there? There doesn't appear to be a file there. I'd like to know more about what just happened, so I am going to use Windows Explorer, which I happen to have open already, and sort by last modified. There's my file. It's got nothing in it. It's empty. So now I'm really concerned. When something like this happens to me as a developer, I want to stop and think, is there anything I could have done earlier to cause this to happen that I'm not aware of? In other words, did I run some other cell way up here that changed the behavior of this cell? So I'm going to run the whole thing again. Just start from the top, restart the kernel, run every cell from top to bottom. Cross my fingers. Okay, the plot appeared at the bottom. That's good. And what about my plot file? myplot.png. I've got it spelled correctly. Nothing in it. Nothing in it. So I'm confused now. What if I verify that in Windows? Is it still there? It's still there. Nothing in it. It's empty. Where did the plot go? The next thing I would do as a developer is start removing things. Is something I'm running having an unintended effect? The first thing I'm going to remove is the show, because I don't need the show if all I want to do is store it to the disk. I'm going to comment out the show. Let's try to run this cell again now. Let's do even one step more. Let's just do one step at a time. Let's comment out the show. What do we get now? Okay, we got our plot. That looks good. We got this that says a minute ago. Maybe that will switch to a few seconds. Yeah, there, it switched to seconds ago. There it goes. So there appears to be some kind of discrepancy between running it and calling show and then running it and calling save. They don't appear to play nicely together, at least in this circumstance. Let's see if we can reproduce the problem. I will uncomment out the show. Try anyway. Okay. And let's delete this output in case it's confusing. Delete the output. The output's gone. We're back to where we were at the beginning. We have a call to show, then we have a call to save, one after the other. And we'll delete the myplot.ping just to remove any confusion there. Okay. What we'd like to see now, we'd like to see the output in the notebook of the plot, and we'd like to see the appearance of this file in our directory. Well, there's the output. Waiting, waiting, waiting. Don't see the file. Oh, there it is. And it does say seconds ago, so it was just created. Now if I try to open it, it's empty. And if I try to go to the directory in Windows, it's blank. It's empty. So there seems to be some kind of weird interaction between the show and the save. What if I reverse those? What if I do the save first and then the show? Because remember, the plot is actually what creates the image. We just haven't displayed it yet. So we have it hidden in memory, but we haven't painted it onto the notebook. But now we're saying save it first, then show it. And let's reset ourselves a little bit. We'll delete our file. And we'll delete our output. Delete clear output. Okay. We've got a minimal example. All it does is create a data set, call the plot function, call save, and then call show. Let's see what happens. Well, the show worked. Now what's going on over here? Anything? Are we waiting for our file to appear? What we're actually waiting for is for Jupyter Notebook to notice there's a file. It doesn't take that long to create the file. It's just that the Jupyter Lab programming doesn't immediately detect the presence of that file. Let's see what happens now. Oh, there it is. Okay, so we have learned that the save preceding the show has much better chance of success than the save following the show. And I would challenge you, this is well beyond the scope of this course, I would challenge you to try to figure out why that's happening. And I would love to hear back from you. If you can tell me why, if I have these in the reverse order that they are now, we get an empty graphics file on the disk. We don't get an error, but we get an empty file. Very curious. Throw that out as a challenge for those of you interested in taking it up. And that brings us to the end of our slideshow, I think. Oh, I was just demonstrating here on slide 11 some of my quote-unquote research to do things like this. And I strongly encourage you to build these habits. How do I plot a bar chart with a data frame in Matplotlib Python? And you can find examples that you can adapt to your situation to get your work done. And on the following slide is another tutorial of sorts that I found useful. If you'd like to take a look at that, it taught me a lot when I was learning this technology to begin with, and it might help you as well. With that, we will adjourn. Thank you very much.